variables, and let me tell you this: if x is a random variable, okay, and y depend on s, okay, and we're seeking. If I know the probability distribution of x, how can we derive the probability distribution of y? It's just like maybe s has to do with let me just say the numbers of hours that we use in a company to generate to produce, and uh, that vary and the cost. Maybe the cost of production is y that depend on s. If the hours varies, then the cost also going to vary. So if I know the probability distribution of time, can I figure out the probability distribution of the cost? And that's what we want to do now. We got three methods. If you want to do this, one is the method of distribution function. The second is the method of moment generating function. We've done that before. And the third one is the method of transformation. Now, this method is new. Okay, we have different kind of transformation that can be used, but I'm going to use Jacobian transformation. Okay, now let's get started. I'm going to introduce you to the method of distribution function. Now, let me tell you what we want to do. We have identified x. It's a random variable. It has a probability distribution. S could be discrete, it could be continuous, and we now have a new variable y, and that very new variable y is a function of x. Now, if I understand the probability distribution of s, we now want to figure out the probability distribution of y. Does that make sense? That's what we want to do. Now, let's discuss the method of distribution function, and I need you to pay attention. Let u be a function of the random variable y1 up to yn. Now, take a look at this. The original variable could be more than one variable. The original variable that I have is y1, y2 up to yn. The new variable is u, which is depending on these old variables. But let me tell you this, these old variables have their probability distribution. What is our intention here? Okay, knowing the probability distribution of the old variables, can we figure out the probability distribution of the new variable? That's what we want to do. That's what we call function of random variable. So what I'm going to do first, I will define the region U, okay? The region U, which is equal to a realized value, a lowercase u, and that will be in this space. Don't forget, this guy depends, u depends on y1 up to yn. Now, because I want to use the method of distribution function, when I talk about distribution function, you know what I mean? I'm talking about CDF, the cumulative distribution we've done before. Now, when you take a look at this guy now, whenever I want to figure out the CDF, we're actually going to consider that guy, okay? An uppercase u is an uppercase u is a random variable. A lowercase u is a realized value of a random variable. Now, the moment I get that, then if I find a probability associated with that, then I'm actually talking about the CDF. You remember we've done CDF before, an uppercase u, okay? And let me tell you this. You know, the moment I get the CDF, to be able to get a PDF or a PMF, like for instance, if u is continuous, if I have a CDF, okay, if I want to get a PDF, then I'm actually going to perform this. That's why I said by integrating this over the region, okay, and after getting my CDF, then if I want to get my PDF, I'm just going to differentiate. Now, to get a CDF requires that I integrate a perform antiderivative, and if I want to get the PDF, which is a lowercase f of u, then I'm going to differentiate the CDF. So now, using the method of distribution function, what we normally want to figure out is to first get the CDF. The moment we get the CDF, then we can differentiate the CDF to be able to get the PDF. So what we're looking for is the PDF, the lowercase f. And I'm going to demonstrate now. I'm going to have an example. Take a look at this. A process for refining sugar yield up to 1 ton of pure sugar per day, but the actual amount produced Y is a random variable because of machine breakdowns and other slowdown. Suppose that Y has a density function. Now, if you take a look at what we have here, Y here, I'm actually going to refer to it as an old variable. Okay, it has a PDF, 2Y. Okay, now they want to define a new variable right now. Take a look at the new variable. The company is paid at the rate of $300 per ton for the refined sugar, but it also has a fixed overhead cost of $100 per day. Thus, the daily profit in hundreds of dollars is given as this. Now, let me tell you this: U is the daily profit, and it's a random variable. And you can see U here depends on Y. Y is the old variable, U is the new variable. So if Y is a random variable, a function of a random variable is also a random variable. Does that make sense? Now, you know what I want to do now? We want to find the probability density function of U, which is a lowercase f of U. That's what we want to figure out. How are we going to do this? Let me tell you, we got a lot of method that we can use that will give us the same results. But I want to first demonstrate how the method of distribution function can be used. Now, the very first thing I'm going to do if I want to find a method of distribution function, I'm actually going to start with this. Take a look at that. That will center on the new variable U. The probability of an uppercase U, less or equal to that. Now, my uppercase U is actually going to be the function that I was given. Take a look at it. 3y, U equal 3y minus 1. What I'm going to do right now, I'm actually plugging that in here. Take a look at that. I've already plugged in 3y, whatever function given to replace an uppercase U. That's what I've done. And after that, you know what I'm going to do? I'm actually going to solve for y. Solving for y will lead me to this. Is there any question at this time? How we're able to get to this junction? Is there any question? Now I solve for y. When I solve for y right now, what do I want to do now? Why do I need to solve for y? Why do I need this? Because if I don't actually base my random variable on y, there is no way I will be able to use the old function. There's no way I will be able to use this. I want a situation where I'm gonna use f of y, and therefore I need to first do what I'm doing at the moment. Now I want to find the probability of y less or equal to this guy right now. If I want to find that, then it means I'm actually going to be coming from a lower bound to that particular. Take a look at this guy here. Do you see that? But I want to find the probability of y less or equal to this. And that's going to start from the lower bound. This is the lower bound ever, but you have to use the lower bound in the question. Of course, if you want to see the lower bound, you can come back here. You see the lower bound here, 0. Whatever lower bound given. Okay? Now the moment you do that, you're actually going to find yourself here. Okay, I'm just plugging in 2y for f of y. Then what am I going to do? I'll perform an antiderivative on 2y. 2y, that will be 2y squared over 2. That will be y squared, right? If I have y squared, what am I going to do? Okay, I'm going to plug in the whole of this guy to represent y. Okay, don't forget here, I'm going to have a y squared. Okay, it's going to be this guy squared, and I'm plugging 0 when I'm minus. I'm still going to have this guy. Okay, so what my CDF give me now, my CDF actually give me this guy. Is there any question about how I got the CDF? Now I want to take you back. How do we normally present the CDF when we got the CDF? Do you remember this guy? Do you remember this guy that I said? Whenever you get your CDF, we present the CDF this way. You're going to be bounded 0. 0, you're actually going to go over the range. You know, the moment it is not this, if you're presenting CDF, okay, it's going to be 0 here, it's going to be 1 here. Whatever you get is going to be in the middle, and you specify. Now, there's another thing I needed to pay attention to. Initially, the state space for Y was 0 to 1. But right now, we are no longer working with Y. We are now working with U. Therefore, I need to redefine my state space. Okay. Now, if you actually want to redefine the state space right now, that is exactly what I'm doing here. That is exactly what I'm doing here. Okay. That's exactly what I'm doing here. Okay. So what I'm trying to tell the world right now is that if Y lie between 0 and 1, then the 1 for you, okay, is actually going to lie between that. Now, if you take a look at what you have from here, I said if U is less than -1, okay, then the U plus 1 over 3 will be less than 0. I want you to take a look at that. Okay, this is going to be less than 0. Then we're going to have that. We're going to have that. So at the end of the day, I was able to define my U to be between this and this. And what you can do, if you really want to solve that, is that since you already know the initial range of 0, 1, you can just plug in and find and solve for U. Okay, and when you solve for U, okay, you can do it right here. This is going to be super cool here. Take a look at this. To me, that is looking like U equal to 3Y minus 1. Okay, now what is the lower bound of Y? Let's come back here. What is the lower bound of Y? 0, right? Let us plug in 0. If you plug in 0 here, that will give you -1, right? That will give you -1. If you plug in 1, what are you going to have? If you plug in 1, okay, if you plug in 1, that would be 3 times 1 minus 1. That would be 2. That was why you got this new upper bound and the new lower bound. Okay, now after, the last thing you're going to do is to differentiate the CDF. I want to differentiate this guy now. Okay, so differentiating this guy now will give us this, which is what we're looking for. Okay, you can see what I've done. We're going to differentiate this guy to be able to have the PDF we're looking for. Now we're done. This is the PDF. Okay. Now, if I want to answer a question that has to do with the mean of the profit, the variance of the profit, this is what I'm going to use. Because here, profit, this is a probability distribution for profits. Does that make sense? If I want to find the expected value of U, the variance of U, I'm actually going to use that. And if I'm going to use that, then don't forget I'm always going to use from -1 to 2. Is there any question about this?